So we've learned already the first derivative test. The first derivative test was if you can find out where your first derivative is equal to 0, maybe it's at 2 points, and if it's increasing before and decreasing after, that makes -7 a maximum. If it's decreasing before and increasing after, that makes 3 a local minimum. That's the first derivative test. The first derivative test only looks at the first derivative to find out if something's a maximum or a minimum. The second derivative test looks at the second derivative to find out if something is a maximum or a minimum. What you do with the second derivative test is you start off the same way and you say, I find out that my first derivative is equal to 0 at -7 and 3. And most people forget the second derivative test because you will so naturally go to making these arrows that you will already know that -7 is a max and 3 is a min from your first derivative test. But sometimes on the IB exam, they say, we want you to show that you understand the second derivative test. The second derivative test says, if you've figured out where your first derivative is equal to 0 at -7 and 3, and then you figured out where your second derivative was equal to 0, and let's say in this case it's equal to 0 at -1. And with your second derivative, you figured out that this section was negative, so it's concave down, and this section is positive, so it's concave up. Even if you didn't complete the first derivative test, this is going to be enough information for you to tell that -7 has to be a maximum. Can you see that if it's concave up like this, the only way that it could be flat is if it was at a maximum. The only way that your first derivative could equal 0, meaning your tangent line is flat, is if that was a maximum. And the only way that you could tell at 3 that this has to be a minimum if it's concave up like this, the only way your tangent is ever equal to 0 is if it's at a minimum. So the second derivative test says all you have to do to show something's a maximum or a minimum is find out your first derivative is 0. So that's your first job. Find out your first derivative is 0. Then, if at that point your second derivative is bigger than 0, and if it's bigger than 0, it's going to be concave up at that point, then it has to be a minimum. If you find out your first derivative is equal to 0 and your second derivative at that point is concave down, then it has to be a local, oops. Is it fixed on yours? Or does it say minimum for both of them? Yeah, the second one should be maximum. Because if it's concave down, the only way you can have your first derivative equal to 0 is if it's a maximum. Algebraically, this is actually a really quick way, and often is quicker than the first derivative test. Because all you have to do is find out where your first derivative is equal to 0, and then check, is my second derivative positive or negative? So we're going to use the second derivative test to find stationary points for these ones. So we find our first and second derivatives. We set our first derivative equal to 0 to find out possibilities. We know that the slope of the tangent is equal to 0 when x is equal to 0 and x is equal to 2. look at our first point, which happens to be, if we want to find the actual coordinates of that point, we could plug 0 back into our original equation and find out that we have 0, -2 is the actual point on our original graph. Then if we find out what the second derivative is equal to at 0, we find out it's equal to -6. -6 means that it's concave down, and it has to be a local max. Point number 2, find out what the actual coordinates are on your graph. When you plug 2 into your second derivative, it's equal to +6, meaning that it's concave up, so it has to be a local minimum. Here's a little sketch of what that graph looks like. So to recap, what does the second derivative test need to find out if something's a maximum or a minimum? You need 2 things. You need to show that the first derivative is equal to 0, because that has to be true for any max or min. And then secondly, you have to find out if it's concave up or concave down at that point. And if it's concave up, it's going to be a local minimum. If it's concave down, it's going to be a local maximum. Now, the reason most people forget about the second derivative test is because when you're working through this, and in examples that we're going to do, you are going to naturally do your first derivative, draw your number line out, find out where things are increasing and decreasing, and do your first derivative right away, your first derivative test, and then you don't even need to do your second derivative test because you already know that if I had drawn my number line and included 0 and 2, I would have found out that it was increasing, then decreasing, then increasing. And if that's the case, what has to happen at 0? It has to be a local max. What has to happen at 2? It has to be a local min. You will also do your number line when you graph this for your second derivative. Can you see that it's equal to 0 when x is equal to 1 in your second derivative? And if you tried something before 1, it would be negative, concave down. Anything after 1 is positive, concave up. And if you wanted to find out what that point is, you'd plug 1 into your original equation, and you could label that point. 1, -4, something like that. That's ugly 4, isn't it? Okay, so try the second derivative test for this one, and the next couple as well. Here, I'll put the answer up for this one so you can check. I'll move it down in a bit. There's the first 2 points. I'll put the third one up. So the second and the third points, we have concave down and concave up. But since our first point, the second derivative is also equal to 0, all that tells us that it's got to be a stationary point of inflection. So our first derivative tells us that we're going to have 3 stationary points, and then our second derivative classifies them. There's our first and second derivatives and simplified. and then the only place that the first derivative is equal to 0 is at -1. So your point is -1 comma -1 over e. And at -1, your second derivative is positive, concave up, which means if it's concave up and you have a point on there, again, I always like to draw the picture because if it's concave up and you have a point on there, what does that mean? It has to be a minimum. Yes?
What was the review you gave us for the exam? Is there questions on there which is helpful?
So using the quotient rule and simplifying it, your first derivative is -2x over x squared plus 1 all squared. And then using the quotient rule again and simplifying it, your second derivative becomes 6x squared minus 2 over x squared plus 1 cubed. So now, when you want to find your first derivative, when is it equal to 0? Remember that a fraction is only equal to 0 if the numerator is equal to 0. So we need to find out when is -2x equal to 0, and that happens when x is 0. Plug 0 back into our original function, and we find out that the point is 0, 1. Plug that same x value into your second derivative, and you get -2, meaning that it is concave down. What kind of point is it then? It has to be a local max. We'll do one more example so that we finish up this section. So here we have a cubic graph. Part of the graph is shown with a maximum at m and an inflection point at n. Find f prime of x. That's just a straightforward derivative. Now, if we want to find the x coordinate of m, we're going to factor it. And factoring it, you don't even have to do the sign diagram to find first derivative test or second derivative test. According to that diagram, the only possibility for m would be x equals -5. Find the x coordinate of n, well then we need to find our second derivative, set it equal to 0, and x is equal to -2. Now, the line L is tangent to this curve at 3, 12. Find the equation of the line in y equals ax plus b. So we'll find often on an exam question, this is an old exam question, that they ask a bunch of different things from different sections of the unit all in one question. So we have the first derivative, the second derivative, and now we're finding the equation of a tangent. So how do we find the slope of our tangent line? We plug 3 into our first derivative. So when x is 3, our first derivative is equal to 16. That would be the slope of our tangent. And now that we have the slope and a point, we can plug that into either y equals mx plus b or our slope-intercept form of the line, simplify, and we get the equation of the line.